Okay, YouTube, in this video we're going to be looking at dividing rational expressions as opposed to doing what we did in our last video, which was multiply rational expressions. So what I want to mention here essentially is that, again, just like multiplying rational expressions, dividing rational expressions with, I guess, variable expressions is very similar to doing this with just real numbers. So that is to say, if we had a couple of rational expressions, say a over b divided by c over d, the idea is that we instead just multiply by the reciprocal. So what we're going to end up doing is really multiplying every time we have a division problem involving rational expressions. So when it comes down to it, what we need to be really good at is essentially just rewriting it as multiplication. So if a, b, c, and d, we say our expressions where our b and c and d, these things here, b and c and d, do not equal 0. Now, why can't c equal 0? Well, because when you look at it this way, c is going to be rewritten as a reciprocal, or in the denominator here, with our reciprocal product. So we're going to have to restrict that as well. So looking at an example here of something like this, we would just say, well, if we had 7 over x plus 1 divided by x plus 2 over 2x minus 3, well, first thing we would do is factor it, but we would also rewrite this as just multiplied by the reciprocal. So multiplying by the reciprocal looks like multiplying straight across. We get 7 times 2x minus 3 over x plus 1, x plus 2, and it looks like we had no common factors here. So in terms of restrictions, they say x cannot be equal to 3/2. And so this is something I want to talk about here. They only list one restriction, but what I want to do is I actually want to make sure that when we look at this right here, we'd say that this, okay, cannot equal 0, and this cannot equal 0. So if x plus 1 equals 0, then x equals negative 1. If 2x minus 3 equals 0, check it out, 2x minus 3, set that equal to 0. This one involves a two-step process. We would say we get x equals 3/2. So with our initial expression, x cannot be equal to 3/2 or negative 1. Now when we rewrite this, you'll notice that in our final expression here, we also have an x plus 2 down here. So we also have to check our final expression, and looking at it, we would say that x plus 2, this cannot equal 0 either, because in our final expression this was down in its denominator. So if x plus 2 equals 0, then x equals negative 2. We would say that these are all the restricted values from our domain. So let's take a look at a couple of examples of our own. You can try some on your own, but let's break it down into a process. I suppose we would factor to restrict domain. Okay, 3, this will be an additional step. It only applies to division, but rewrite as a multiplication expression by the reciprocal of the thing we were dividing by, so the divisor. And then what we'll do is just multiply and simplify. Multiply, simplify. So we'll look at our very own example here. Let's take a look at it. Whoops. Okay, so look in here. We have finding the quotient between these two rational expressions. I suppose that the first thing I'm interested in doing is factoring both sides. So it looks like on top here, 7 times x, there's no more factoring than we could really do with this, but the 2x and the 10 here, looks like they have a common factor of 2. So we'll take out a 2. This leaves us with x minus 5 here. And what we have is dividing by now this expression where we have a common factor of x up top, x times x minus 6. And with this being a trinomial where our a value is 1, we're saying we're looking for two factors of positive 30 that add up to be a negative 11. So if they are multiplying out to be a positive, they have to have the same signs. And since they add up to be a negative, they both have to be negative. So I'm thinking negative 6 and negative 5 here. So with what we see, what we are going to do is now take this and hopefully we'll restrict its domain first. Don't want to forget to do this domain. We would say all x values such that x cannot be equal to what? Well, if we set everything in this denominator equal to 0, why don't we do that here? If you set 2 times x minus 5 equal to 0, we would divide both sides by 2. So we would get x minus 5 still equals 0, and then x equals 5. So we cannot use an x value of 5. Also over here, we would say setting these equal to 0, we're also going to get 5 and 6. So we would say 5 and 6 must be restricted from our domain. Now, what we're going to do next is essentially we're just going to rewrite these expressions, and instead of dividing, okay, which is what we're currently doing, we're going to be multiplying by the reciprocal. So that means that this x minus 6 and this x minus 5 now are in the numerator, and our x minus 6 is now in the denominator. So to simplify this, of course, we would multiply it first. So on top we get 7 times x minus 6 times x minus 5, okay, all over 2 times x minus 5 times x times x minus 6. And so looking at what we have some common factors here that readily cancel out. Even our x and this x here cancel out. So what we get left with is 7 over 2, and we would say that x is not allowed to be any of these things, 5 or 6. You can't do this. This is out of our domain. So for this last example we're going to look at here, essentially what I want you to see is, well, what do you do when you divide by a polynomial? And again, just like in our last video, what we're going to do is we're just going to station this over a 1. So let's go ahead and work on factoring these expressions if we are able to factor them. So I notice that on the left here, at least the denominator, 4 times x squared. If we wanted to rip this apart into 2 times x, you could. But I want you to see that that's something right there that we can go ahead and leave as just like a 4x squared. Now the top, I notice that this one here, this actually has an a value that is not equal to 1. So in terms of factoring something like this, we're going to have to do a little bit of guess and check. So looking at our guess and check here, I suppose that the first thing we want to do with our FOIL, okay, when your a value is not 1, is guarantee that you get the 6x squared in the front. So since this is the reverse of FOIL, we say, well, what are the two things I could put here and here and multiply first that would give me a 6x squared? And I can think of two things, either a 6x and an x, or we could have done a 3x and a 2x. What I'm going to do is always encourage you to choose the closest two factors to one another. So now we have the 6x squared. We say, what are some things that would multiply out to be a negative 15? So perhaps we'd have like a negative 5 and a positive 3, something like this. This would definitely give us a negative 15 in the back. The only question is, do we get this 1 in the middle? So to do this, we check our O and our I. That is, we check our outer and our inner multiplication. What I notice here is I get 3x times 3 is 9x. And if we were to take negative 5 times 2x, we would get negative 10x. This actually adds up to be a negative x, which is the opposite of what I want to have here. So really the whole secret's going to lie in, well, those signs didn't work there. We'll just switch our signs around, and what we end up with is this right here, 3x plus 5 times 2x minus 3. And checking our outer and inner, because it'll switch these signs here, we'll end up with a positive x there as our sum in the middle term. So here's our factored form of this first part of this, and we say dividing by, now over here I notice they share a common factor of x. So we get left with 3x plus 5 here, and this is all over 1. So now that we've done this, let's go ahead and rewrite this as multiplication by the reciprocal. So we have 3x plus 5, 2x minus 3, all over 4x squared. And this is times now 1 over x times 3x plus 5. So as we normally do at this point, we're going to go ahead and multiply these fractions straight across. And what we end up with is 3x plus 5, 2x minus 3 times 1. And in the denominator here, we get 4 times x squared times x times 3x plus 5. So looking at what we're dealing with here, we already readily notice that the 3x's plus 5 cancel out, and also that this x squared times x, we could rewrite this really as a 4x cubed. So our simplest form or simplified form of this rational expression would be 2x minus 3 over 4x cubed here. So this number over this factored expression. And you could see here that x, if we were to set 4x cubed equal to 0 and solve it, that is divide by 4, we would get x cubed equals 0. We'll take a cube root of both sides. When we take a cube root of both sides, the cube root of 0 is 0. So one thing that we need to make sure that we do here is restrict its domain to exclude 0, which, by the way, I must have gotten a little carried away. This is something that we didn't check when I did factor these expressions. So when we look up here, okay, looking up here, we say look at this, look at this. We don't want these to be 0. So since they cannot be equal to 0 here, we'll set each equal to 0 and solve them. But you'll notice that we, by setting this equal to 0, get x equals 0. And so that is one of our domain values that we've excluded there. And nothing would cause 1 to be 0 here. So we've found our exclusion. So dividing with rational expressions, really we're just going to rewrite as multiplied by the reciprocal, and we're going to multiply instead. Cheers.